Good morning, friends. Welcome to Eastern Academy. And today we are going to discuss about understanding 8085. So, why we have taken 8085 have lots of reason. So today is a week one and the day one and the session one. This will have a two session every week. One is at 11 to 1, 12. Other one is 12 to 1. So two sessions. And as usual, you can contact me on my mobile number and everything, whatever you have a doubt. And why we have selected 8085? That's multiple reason. The first reason is generally this is discussed in the colleges. Still, it is there in the college syllabus. Even a GATE, I think it's there in a GATE also. So this is still the talk of the town. So it is used in the college syllabus everywhere. That is one reason. And second reason is this is a quite popular microprocessor for quite long time in the industry. That's the second reason. And the third reason is there's one microprocessor you can understand 100% from start to end. I mean, that is 8085. If you take every other processor, they will become too big. If you go to 8086 or some other processors, actually along with 8085 there were so many processors. One is called 6502, another is called 6800 from Motorola, the other one is called Z80 from Zilog. There were so many things, but because of sheer popularity, 8085 took the market. And so if you understand 8085, understanding every microprocessor become easy. And the next most important reason was this is directly attached to our course. How? After we complete the 55 problems, the C problems, the next problem is going to be writing an assembler for 8085. Okay. So you'll be able to convert the assembly code of 8085 into machine code of 8085. You'll be writing an assembler. Okay. That if you understand the assembler, later you can start writing a small compilers. But assembler is the first one to make you to understand how do people have all the questions. Who will convert my instructions into machine code? So you can do that. If you do it on 8085, you can write it on 8051 or ARM or anything. And the second one is after the assembler. Normally we think we are going to create the microprocessor only in silicon. Okay, but you are going to create a 8085 on a software. Okay, on a software that is called simulation. You're going to say that means that your software will act as a 8085 microprocessor. So when you write a machine code, if you compile it, if you assemble it using your assembler, they're going to execute in your software. That means that you will thoroughly understand how the 8085 works. That means that indirectly you will understand how a microprocessor works. That will help you to understand ARM, everything which we are going to discuss next. So with so many reasons, I have selected this 8085. Okay, so today, as a first thing, the most important in every microprocessor is not the architecture or anything. They're all next. First, you should understand the pinouts. The pinout will tell you that what the microprocessor supports. That's it. If you see the pin, nothing can be done beyond that microprocessor with the external world. Okay, so that is the thing we are going to discuss. That is 8085 pinouts. And this is what the typically 8085 Intel's microprocessor. You know the year 1976, roughly about 45 years, but it changed the world really good. It is a 8085. That everything is having a meaning. P means a plastic package or a ceramic package, and A means which revision it is. H means what speed it is. and 1, 2, 3 will tell you the what are the various revisions. All the things. Forget about that. For us, the important is number 8085 is a number. Now, see the pins. It's about how many pins? About 20 pins on this side, 20 pin on that side. This is a 40 pin IC. This is a 40 pin IC. Okay. This IC was built by Intel. Okay. Intel was famous in integrated circuits. So what they did was, this is what the circuit. See that? It's quite complex for you, but they did it. Intel did it on a big tracing paper, all these things. That is what they are very popular. Okay. So this is actually your 8085 microprocessor inside the silicon. Okay. Let us zoom it. If you zoom the next level, you are getting this small connections, everything. Still, if you zoom it, you will see that you will see the connections. Okay. So these are all the way the chips are connected. That's the way they made the chip. See that it's all connection. Okay. And one is horizontal, one is vertical connections. And these are all various blocks on silicon, the bottom. This we will see in our later date VLSI session thoroughly, how ICs are fabricated, how ICs are doing from the basic, from a SAN to IC, we will do that. Okay, that you can see a lot of videos in the YouTube, but we will also discuss for our part. Okay, now the trick here is, this is the way we represent. Ultimately, this is the way we represent the chip. See here, this is about 40 pins, 1 to 40. If you understand all the 40 pins, then you understand the microprocessor. That's it. How it is connected to the outside world. Okay. That is what we are going to discuss today. What are these 40 pins and how these 40 pins are connected outside. And already we have discussed about what is microprocessor, everything. What are the variations of 8085? And don't worry about this. They always write 8085A because when they did the first 8085, it has some bug. So they came out immediately with the 8085A. So they always mark it. So all the data sheet everywhere you will see always 8085A. You will never see 8085 at all because that processor did not get released at all. Only the processor which got released got 8085. So we are going to discuss about the pin nodes. Understand this is about 40 pins. You should thoroughly understand this 40 pins. That's a trick. If you understand the 40 pins thoroughly, okay, then you're done. And we will also discuss some pins have bar. See that WR bar, RD bar, M bar, and reset in bar, INTA bar. We will discuss about what is the meaning of the bar also. Why it was there those days. Even today is that, but I'll give you the reason of it. Okay, so now let us get into the board as usual, and we will discuss about what are the pin nodes. And most of them is all what we discussed, and let us see the thing, how is it. The one trick is, once you understand one processor, understanding other processor generally easy. So don't it will not be very difficult. Okay, you need to understand that. See, we discussed first about general microprocessor, and then today we are going to see about what is the variation on 80 That's it. Once you understand the variation, then you are done. We have discussed about general processor. Let us go back to general processor. What we discussed on general processor? It has address lines. It has read. It has write. It has data. That's all. Nothing more than that. Every microprocessor talk to the external world only with this. Nothing more than that. Address used to point a memory, and read is used to read the data. Write is used to write the data, and data is to get the actual data in and out. And always make sure that all these things are given by microprocessor, and only data he gives or accepts. Nothing more than that. And there is a power pin. Okay, there is a power pin. There is a ground power supply. Then there is a reset. Then there is a clock. Okay. We will discuss about clock later because some of you know about clock, others may not be knowing clock. We'll discuss about clock later. And reset is the one which equivalent to microprocessor starting from a start initial thing. So the moment you give a 5-volt supply, see here, the moment you give a switch, the moment you press the switch, see, let me write here VCC, sir, because there's a reason for that. When I say VCC, it could be any voltage, 5 voltage or 3.3 volt or 2.5 volt or 1.8 volt. It could be anything. But okay, so thanks. Okay. So the moment I put the switch on, then the microprocessor will start from start address. The start address could be anything. That's why I written start address. It could be 000 or it could be FFFF 0 or FFFF 000 or FFF anything. Don't say that this has to be a starting address. That is defined by the microprocessor manufacturer. That is defined by the microprocessor manufacturer. You do not have the control over the this one. Now, the trick is there were few more extra features. One feature is called interrupt. It gives interrupt. It gives interrupt acknowledge. Another feature is called DMA request, called DMA acknowledge. We'll discuss this later. This is what the generic processor, where we will see that what are the variations of a 8085. Okay, 8085 has 16 address lines. How many address lines? 16 address lines. And it has 8 data lines. Okay. Then they had a signal called write. And they have a signal called read. And they have a signal called clock. But if you use the internal clock generator, you can give a crystal outside. You can connect the crystal outside. If you use the crystal outside, it will generate the clock internally. In that time, you should have a X1, X2. Understand? That is, you can give a clock from outside, or we can connect the crystal. Then there is a reset. And there is a power supply. This plus 5 volt. So these are all the your typical microprocessor. They have clock, they have reset, they have a plus 5 volt, and they have an interrupt and interrupt acknowledgement, and they have a DME. Acknowledgement. I'll tell you what this. So this all 8085 also has. Okay. Apart from this, it has so many other extra features. That's a trick. Also, when they added extra features, the number of pins has become increased beyond 40. Beyond 40. In 1976, unfortunately, they did not have a technology to produce more than 40 pin. Okay, it was evolving, it was very expensive. 40 pin producing was cheap, and all the equipments were manufactured to produce 40 pin. That's why if you see all those ICs, their sizes and the thing will be always the pin to pin distance and the size all will be almost same, because they don't have a machinery to manufacture the various types like today. So what 8085 manufacturer Intel thought was, they also got to give a feature and also 40 pin. So they don't have any other methodology. If they reduce a picture, people will not buy it. It become no use. Say if we remove, if we don't use the DIQ, if we don't use interrupt, you will not buy it. So finally, they thought one very nice thing. What they did was, inside the microprocessor, they have address lines. There's a block, there's an address line, A0 to A15, that is 16 address lines. And they have a data lines, 8 data lines. Make it bigger block. So what they did was, okay. Is it? Okay. I don't see the lag because I'm also like a user. I sent to you, I'm getting it back. Is it okay now? Everybody is saying board is lagging. It's the first time I'm taking in the morning. Let me pause it. Let me pause it 1 minute. Okay, now what is happening is this. I have 16 wires in A0 to A15, and I have 8 wires in D0, D15. Okay. Because of this, now we have 8 wires on D0 to D15 and 16 wires on address. See, what they did was, very interestingly, that Intel people, They had taken this address wires, they divided into two groups. One group is A8 to A15. That comes out. The other one is this is only 8 pin. See here, I give 8 plus 8, 16. I come out only with how much? 8. That means that I have a switch here. I have a switch here. Okay. If you on the switch, the address, it become address line. It become A0 to A7. If I off the switch, there's nothing. No connection. No voltage. It's a tri-state. Now, when I make this switch is on, this become D0 to D7. That's why they call this wire as AD0 to AD7. They don't call. Understand? So they also call this line is can be sometime address line, sometime data line. This is called multiplex. But this is only on the old days. This is only in 1976 and not today. In 2021 and all, we don't use this concept. It's gone because today people are making IC of 4,000 pins. How much? 4,000 pins. ICs are available, more than that. So we don't have to worry about making the IC. Okay. Do you feel the lagging now also? I did a small change now. Yeah. Thanks. Yes, I removed the video. So I projected only this board. That is fine. Okay. Now, the trick here is by this, they saved instead of 24 pins, they saved 16 pins. That means that they saved 8 pins. This is it's a great achievement in 1976. You'll be thinking today so simple, but it's a great thing on those days. But the problem is you need address and data. So what they have done is it's a tricky here. What they have done is I have a box. I have a box. There I have the microprocessor which has address line 16, data line 8. I split into 8 and 8. This is A, this is AD. AD0 to AD7, A8 to A15. Okay. Now, the trick is I have a block. You may call this as a mux. What they have done is they put outside the same box, same switch. Okay, see here. When I on the switch, this should be on. When I off the switch, both are off. When I on the switch, this should be on. Am I right? So how do I do that? For that, they have a signal here. They created a signal, the control logic, which comes here. The same signal goes here. Okay. They call that signal as a ALE, address latch enable. What they do here was, whenever I'm giving address, normally this one is data. Whenever I give an address, that time I remove the data, I on the switch, and I put the data. But the problem is that will be there only for shorter time. Then I remove it. So what the microprocessor will do, the microprocessor will give the address on the AD bus only very short time. Very short time. Afterwards, this is going to be data bus. It's going to be address bus for very short time. So what they told you, hey, I give you very short time. You better, what you do? Latch it. So I put a latch. Once again, D flip-flop. Please understand. Once again, D flip-flop. Nothing more than that. Now, I give a signal here called ALE. That goes as a control signal for the D latch. Let us assume that I have a 8 D flip-flop. 8 D flip-flop. All the control signals are connected. They are going to the latch. And these data lines, AD goes here. You know one thing, when the microprocessor will ALE, with the moment giving an address, let us say I'm giving an address 10,000. Let me put another easy number, 1, 2, 3, 4. What will I do here? I will put 1, 2 at the upper bus, address bus, that is A8 to A15. And I put 34 here. So 34 comes here. Then I give ALE. When I give a ALE, this 34 goes out here. But after small time, I'll make it to 0 once again, ALE. Since I make it to 0, this 34 will be removed. But this 34 will be there. So what we are trying to do is, we are trying to demux it. So afterwards, this becomes a data bus. So it's as usual. It is as we discussed all the time. This microprocessor has a 16 address lines and 8 data line. But please understand, instead of putting the mux here, they put it outside because they don't have a space to make 40 pin IC. 40 pin IC. They have to make it. So they want to save the 8 pins. To save the 8 pin, they did it. So now address plus data together, the microprocessor have only 16 pins. Not 16 plus 8, 24. In the case, 16 plus 8 is 16. Done. Now, address, we write here, address plus data, 16 pins. Okay. And because to do multiplex, we added one more pin called ALE, one more pin. Understood? There's one more pin called ALE. Second, as usual, we have a read pin and write pin. But only small difference. What is a small difference? So they write a bar here. That means that normally we think, let us say I have a control signal. Okay, the latch, the read is going as a latch. Normally we have when a write is 1 means it does latch. Now right is 0 means it's latch. It means that it's called active low. If we write like this, please understand the deep meaning here. If we say ALE, if we say right bar, the meaning is ALE means active high. Right bar means active low. That means that when the microprocessor gives 0 volt, that time it is writing, not at 5 volt. When it is 5 volt, it is not writing. When it is 0 volt, it is writing. Why they made it? Why they made the thing as active low in the cases? The reason was those days they were using BJTs most. The BJT, the input pins, AND gate or whatever IC input pins, they have a transistor. Okay. They have multiple gates, multiple pins. They leave it like this. The moment you connect it to ground, okay, it will consume current, it will conduct. The moment you leave it open, it will not consume current. So they leave the pins. That means that whenever I give it, let me give you one thing. The moment I make it as a input as a ground, it will give a current. Who? Your BJT. Whereas if you make it a 5 volt, it will not take current. So what will happen? When you make it a 5 volt, it will consume less current. When you make it 0 volt, it can high current. This we will discuss when we are discussing about our analog things very clearly. Now let's not get into the active low, active high. We'll go to those sections at a separate time. Please understand one thing. It is not there with the latest MOSFETs. The high or low, it doesn't matter today. But whereas in the case of your BJTs, we had this problem. Because of that, those active low came long time back. So active low means when you make an input as a low, it will consume more current. Now what will happen? Let us assume that I have one microprocessor which is connected to multiple ICs. Let's say I connect 4 IC. Normally it is more, I connected 4 IC. This right signal is connected to all of them. Let us assume right is active high. Active high. When it is active high, that means that most of the time this is going to be inactive. I make it active when I am writing. When I don't write, this is going to be 0. If this is 0, all the input pins are 0. So there will be more current will be coming out of the each and every IC or all the inputs. Okay. Because of that, the total current consumption of IC will be high. So they thought how do I reduce it? What they made it was, normally if I make WR bar, it is called active low. That means that normally this is 5 volt. So everywhere it got 5 volt. So there is no current. So since there is no current, it will be very minimal. Only when I'm going to write something to the chip, device 1, I'll make write as a 0. So this is the reason behind the active low and active high. But there were multiple things we discussed. One is called active low, active high, sink current, source current, and open collector, tri-state, and setup time, hold time. These are all the typical terminologies every electronic engineer should know. Okay, active low, active high, sink current, source current, and then open collector and try state, and setup time and hold time. These are all the one asked repeatedly in the interviews. Okay, we will discuss this in our regular session. Not here, not in the microprocessor. Here we assume that if it is active low, it consumes more current. So what the people did was they made it as a active low. So whenever I make it low, only that time that chip will consume a current. Otherwise, all the chip will give a current here. There'll be more current will come here. That's why they made it like this. So write bar and read bar. Now they are about how many pins? 19 pins of gun. 19 pins are discussed. This is the way we should do that. I exactly the methodology which I do. Active low and active high. Okay, I'll discuss later. Let me understand one thing. I will give you one thing. You take a block, let's say AND gate. You put an AND gate and you have two inputs. When the input is 0 or 1, 0 means 0 volt, 1 means 5 volt. Okay, the moment you give 0 volt here, this IC will give more current. The moment it's giving 5 volt, the IC will not consume any current. Then I have to start drawing about the gates. Okay, that's why I told you that this will go to our active session, the class session. When you're discussing as a part of gates, I'll explain this more. Then these are, say there are two things. One are called functionality. Other one is called details. These are called technical details. Right now, I'm discussing about top level functionality. So we'll discuss about, active low means 0 voltage. So now let us assume that this AND gate can be 0 or 1. When you give 5 volt, you get output as a 5. When both are 5 volt, output is 5 volt. That is what we know. That is what we know. But if you go and see the data sheet and electrical characteristics, that they will mention, if the pin is 0 volt, the current output will be, let's say that 1 milliampere. When it is 5 volt, the current input is going to be maybe 100 or 10 or 100 nanoampere. It will be very, very low. So what is happening is, when I make it this as a 0, I'm consuming more current. Now let us assume that I have a microprocessor, one block. Forget about microprocessor, one block, which I connected to multiple gates. You also might have heard, if you're an engineering student, there's something called fan out. Fan out is nothing but one output can get connected to how many inputs. That is decided based on the current. That is decided based on the current. Let us assume that all these guys are going to give when you make it 0, 1 milliampere. When it is 0, 1 milliampere. When it's 0, 1 milliampere. When it is 0, 1 milliampere. That means that if I give 0, okay, all of them are going to pump in the data. Okay, that time what will happen? This guy is going to get more current. How do I avoid it? So what they have done is, they made normal time. let us say that out of 1 second, I write this device only one millisecond. Remaining 999 milliseconds. I'm idle. I'm not doing anything with this chips, right? I'm not doing any right. So if I give active high, I make normally 0 volt. When I give 0 voltage, there'll be current. So think here, normally I give 0 voltage. This guy is going to give 1 milliampere, 1 milliampere, 1 milliampere. I'll get 4 milliampere. Okay. The 4 milliampere, I will get how much time? 999 milliseconds. But when I selected 1 millisecond, I make this is a 5 volt. So in 1 second, 999 milliseconds, I'm getting 4 milliampere. But when I make it high, that's going to be less current. So engineers thought, why not I make this milliseconds less current and this is a high current. So this is that means that when I am using it, I will make it as a 0. When I don't use it, I will make it as a 5 volt. That is against your concept. Generally, we all think that always active high. We think that if I have a LED, if I give 5 volt, LED should glow. Am I right? Let us assume that a simple case. I have a microcontroller which is having a port. If you make it 0 volt, for us, LED should be off. If you make 5 volt, LED should become on. Now I'm telling you one small condition. You know that the LED, I tell you that LED to become on, it requires 20 milliampere. Let's say 10 milliampere. 10 milliampere. How much? 10 milliampere. Now I'm telling you that this output pin, this microcontroller, any microcontroller you take, this output pin, the output pin will give current. That is what? Source. That is, let us say 1 milliampere. And when he gets a current, he can go up to 20 milliampere. That is called sink. Now, please understand, we go back to electrical. Electrical, I have a resistor. If this pin is 5 volt, if this pin is 0 volt, I will give current. If this pin is 0 volt, no current. If this pin is 5 volt, no current. And one more possibility, if this pin is 0 volt, this pin is 5 volt, this is a current. So see, there are 4 possibilities. 5 volt, 0 volt, AB. There are 2 points A and B. A and B can be 0 volt, no current. 5 volt, 0 volt, current go outside, that's called source. Then other one is called 5 volt, no current, because potential difference is 0. And the fourth one is 5 volt, 0 volt. That means the current is going to come in. This is called sink. Now, the microcontroller manufacturer has told you that my source current is 1 milliampere, my sink current is 20 milliampere. How do you connect the LED? If you connect the LED like this, if LED is red LED, this is 2 volt, and you are applying 5 volt here. This is given 3 volts. This we discussed in the class, but I don't say discussing. Then only you will get here how much? 10 milliampere. Fine, you have done a circuit, but it's not correct because this microcontroller manufacturer told you that I can source only how much? 1 milliampere, whereas LED need how many milliampere? 10 milliampere. So this is not the correct circuit. This is a wrong circuit. This is a wrong circuit. So what I have to do here is I should connect the other way. I should connect the other way. I give 5 volt. I connect a LED. I connect a resistor. I connect here. Now this guy is, let us say, 330 ohm. And this is 3 volts. And the LED is 2 volts. Now you see here, when I make it this pin as a 0 volt, this is 5 volt. That is this condition. The current is coming in. How much? 10 milliampere. But I told you that this pin of microcontroller can take 20 milliampere. So this is the correct circuit. But one thing here. See here, when I write 0 here, LED is on. When I give 1 here, that is 5 volt, LED is off. Okay, there we will make this pin as a LED bar. LED bar to tell you that if you make this as a 0, then LED will on. If you make 5 volt, LED will become off. This is called active low. We have this has to be explained here because generally we think that 1 is active high, zero is active low. Sorry, 0 is inactive. 1 is active and 0 is inactive. That is what our general assumption. But in the digital circuit, sometime 0 can be active, 1 can be inactive. That is totally based on the circuits. The engineers, how they design the circuit. With so many reasons are there behind why I have to select 0 or 1. So this is called active high. This is called active low. That's why normally I don't take up this discussion, but since I've taken up here because initially itself we are starting with read bar and write bar. That means that when this microprocessor put, we told that microprocessor will address line as address. Let us say I want to write, if you write a program, character star PTR. PTR is equal to 0x1000. Star PTR is equal to 0x55. That means that I'm writing 55 at 1000. So the microprocessor put the address 1000 and data is 55. That means that 0101, 0101. 55 means that's why I put 0x. Then 100 means that's a binary. But I told you all the time, when you do write means 1, but here is write bar. So you make it 0. That means that now the microprocessor will make this bit as a 0 volt. Now you have to write it to the memory. By chance, if a memory thinks that it's a write and you are giving write bar, then you need to connect the inverter here. This is active low. This is active high. You should convert them to the active low to active high. By chance, your memory is also write bar, then you connect directly. So that depends on how your memory is going to be. That manufacturer tells you. One manufacturer is a write bar, other manufacturer write. Now same way, when you say read bar, I told you the moment you power the microprocessor 5 volt, the microprocessor will give address as 000. And it makes write as a 5 volt because write bar. And read bar, so it makes read bar as a 0 volt. To tell the memory that I'm reading. So previously we discussed 5 volt or 1 means write. Now I'm telling you that when it becomes 0 volt means write. When it becomes 0 volt means read. When both are 5 volt, then I'm not reading, I'm not writing. Understand now, there's a confusion. When I'm writing when I write bar, then when both are 5 volt, I am not doing anything. When I'm writing 0 volt, I'm writing. When reading 0 volt, I'm reading. Both are 5. Normally, both are 5 volt. That is the meaning of active low signal that they used in your 80, 85. So you have to understand that this meaning of the bar. Okay. Is it clear or anything we discuss? Sorry, I've written here. Address data. (16 pins), ALE 1 pin, write bar 1 pin, read bar 1 pin. So you got 19 pins, and supply VCC and ground 1 pin, clock 2 pins, because you can connect the crystal also. That's why we call X1, X2. Totally how many pins? 16 plus 4, 20, 23 pins. Left out is 17 pins. That's the way, see, that's the way you should discuss. What I'm trying to say is that I try to first understand all the 40 pins of the IC, what it does. Okay. Yeah, that's actually an inverter. Actually, that's called inverted output. That is why they put a bar. But here also, here in a signal, when I say A bar, means it is active low signal. The bar does not say AND gate or anything. It tells you that it's the active low. Your AND gate, you have A and A bar. Okay. That is different. But here it's called, when a signal, if the bar means active low, it says that is because some of the signals are active low. That's why I explain this to you now. Same way, there is a signal called reset in. That is also active low. The reset in is also active low because I put a bar here. So this is about now with this another 16 that we explain. But I have to make sure that you understand this 24 signals. I write here itself. So this is what we discussed. All the microprocessors have address line 16, 8 data lines. We have a read and write, and we have a power supply, and we have a reset and clock. Okay. Yeah, we'll discuss about that. So that is not generally there, but here. Yeah, that's quite tricky. That you have to slowly be a hardware designer. Then normally it all depends on the current. It depends on the current. Okay. When I put an active low, how much current that pin will do. When you do active high, it's all, everything is based on current. Nothing more than that. Okay. Active low, active high, decided only on the current. Okay. That I'll explain to you when I come to analog electronics. Why that does not matter in the case of your FET. Because FET is a voltage control device, doesn't matter. But whereas in the case of BJT, it's a current control device. It was there. But nowadays it does not matter much. That also I will explain. But it's a very tricky, man. Without this, if you have to discuss everything, I have to come here. Then you'll have a problem. That's why I'm not get into the thing. So I just understand the bar now. Enough. So with this is what we discuss, general microprocessor. Now In 8085, what is the difference? This 16 plus 8 supposed to be 24. Now in 8085, it is only 16 because we multiplex address and data. So lower address and data, that is A0 to A15 and D0 to D7. When it is coming out in 8085, it comes out as A0 to, sorry, A8 to A15 and AD0 to AD7. That's a very good question, that which factors affecting. That has to be discussed. We'll keep it up. We will do it. But that I don't need to do it now. That requires a lot of things about analog. Or you should know thoroughly about all the transistor types. Then VCC and ground. Here it is 5 volt. Okay, normal microprocessor can be any voltage, but in 8085, this is 5 volt. That's why they also called 8085. The 5 in 8085 represent the 5 volt. That's another name. The 8085 5 is if this 8 represents the 8-bit. This 8 represents the 8-bit microprocessor. Okay. Now, we will discuss over the remaining 16 pins. Okay, let's take a small break for about 2 minutes. We'll come back then.